Hello students, welcome back. So now we're going to go into the meat of our first lecture in this new online platform. This is a lecture about the normal distribution. Now before we get into the normal distribution, let's have a quick reminder about continuous random variables. Remember, the fact that it's continuous means that there are an infinite number of possible values that can be represented by an interval, a specific interval on the number line. And an example that we give here is that the time spent studying can be any number between 0 and 24. What it means that it's continuous is that basically there is an uncountably infinite number of possible values in any interval that we pick along this set of values for x. And the way to understand what uncountable means is you can pick any two numbers as close as you want to put them together, and I can always find another number that's in between them. So there's no way to count up all the possible values. There's an infinite number of possible values that x could take in any specific interval that you pick, no matter where it is along this line. Now, the continuous probability distribution then is just a probability distribution of a continuous random variable. The normal distribution is the distribution you've probably heard about for most of your life. It's otherwise known as the bell curve. It's a continuous probability distribution for a random variable x. It's the most important continuous probability distribution in statistics, and everything we do with inferential statistics for the remainder of the semester is going to be based on the normal distribution. And the graph of the normal distribution is called the normal curve. Callie, if you're listening, you have these in your slide packet. So basically that beautiful bell curve. And why is it called a bell curve? Well, because it's shaped like a bell. Ha ha ha. All right. So what are some of the properties of the normal distribution? Well, first of all, this is a perfectly symmetric distribution. So the mean, the median, and the mode are all going to be equal, all there right in the center. The normal curve is bell-shaped and it's symmetric about that mean. And the total area under the normal curve is equal to 1. Now, in my last video, we talked about the fact that we're going to be measuring probabilities by taking chunks of area from underneath the curve. So it makes sense that the total area has to equal 1 because that would be 100% of the probability. The normal curve approaches but never touches the axis as it extends farther and farther away from the mean. So basically, x can take any values from negative infinity to positive infinity. Now, there is a special relationship between the mean and the standard deviation for the normal distribution. In the plot that they give you on this slide, you'll see that there are these 2 points called inflection points. That is where the curve goes from concave, meaning it's facing up like a bowl, to convex, meaning it's facing down like an umbrella. So those inflection points are at a very specific place in the normal distribution. They are exactly 1 standard deviation below and 1 standard deviation above the mean. So when you're looking at the normal distribution, you know as soon as you hit that inflection point that that's about 1 standard deviation away from the center. Now, some specific characteristics of normal distributions in general. A normal distribution can have any mean and any positive standard deviation. The mean is going to give the location of that line of symmetry right down the center of the bell curve. And the standard deviation is going to describe how spread out the data are or the bell curve is. Okay, so here are 3 examples. In each of these examples, we've marked the inflection points. Again, Callie, you have these, I believe, as 3 different graphics in your packet. And so for the first one, you can see that the curve is mostly flat. It's a little bit skinnier for the second one, and that indicates a smaller standard deviation. However, if you look at the first and second one, you'll see that they both have about the same mean. Now, between the second and third one, the standard deviation stays the same, but the mean changes. And in fact, the mean is 3.5 for the first 2 curves for A and B, but for C it's 1.5. And then the standard deviation is 1.5 for the first curve, and for the second and third curve, it's 0.7. So because this is my lecture, and because you know I have to ask you questions, I am going to now ask you to look at this example, and I'm going to give you a pause. I want you to figure out which normal curve has the greatest mean, A or B. You ready? Okay, did you figure it out? The solution is A. Curve A has the greatest mean, right? Because curve A has a mean right around 15, and curve B has a mean right around 12. Now, what about which one has the greatest standard deviation, A or B? If you guessed B, you are correct. Okay, B is more spread out than curve A. Usually people get these concepts pretty quickly. Okay, let's do an example. A scale test scores for the New York State Grade 8 mathematics tests are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? And estimate the standard deviation. So where are we going to look for that mean test score? If you guessed somewhere right around here, you are correct. Somewhere right around the center is where that mean is going to be. It's that line of symmetry. And in fact, because the normal curve is symmetric about the mean, we can estimate that mu is about 675 in this case. Now, what about estimating the standard deviation? That's a little more complicated, but basically we're going to look for those inflection points. That's the place where we go from having a cup to an umbrella, or from convex to concave. And then we're going to look at the distance between that point and the mean in the center. And that distance is going to be approximately our standard deviation. And I believe, in fact, that the slide will tell us that because the inflection points are one standard deviation from the mean, you can estimate that sigma is approximately 35 in this example. We are going to move on to the standard normal distribution in the next video. See you there.